Hello folks, and welcome to Rational Science. Today we're going to be talking about phonons and whether they're rational. Okay? And so here's the question of the day that I want to try to answer for you to keep track and follow my train of thought. Okay? Question of the day, are pseudo and quasi particles rational? And there you see the criteria for irrationality that I'm going to use. Okay, and it's if you reify a concept, you turn it into something concrete and think you're moving something real around when all you're moving is an abstract concept. Okay, like love. And I guess you turn it into a heart and you begin to move the heart around and you're saying, oh, I'm moving love. No, you're moving a heart. That's not love. Love is something else. And that sort of thing. Okay. And there are other criteria, not having definitions or using them inconsistently. Okay, the theory doesn't follow from the assumptions, etc., etc. The main one's going to be that first one: reifying concepts, turning a concept into a physical object, and then pretending to move it around. Okay. Okay. Let's go with this next one here. Okay, so what we were doing these last couple weeks is we're looking at how the world originated. Okay, so let's do a little review of that because it does lead into what the subject of today. And the official version today out there is that there was a big bang, an explosion, some 13.8, 14 billion years ago. And it grew into what you see there. We're at the right-hand side of that spilled cup, a cup that's tilted on the ground. Okay. So what you see there are the time slices as you look at it. Okay, as you look at this whole thing, and we're at the right at the edge there of time, which is on the right-hand side. Okay, so this is how they visualize, the mathematicians visualize, this is the explanation they give, the theory they have for how the universe came to be. In other words, there was some kind of explosion billions of years ago, and that evolved through all these little intermediate steps that I covered the other day, and we ended up where we are today, which is the universe we have today with galaxies and stars and atoms and so on. They claim it didn't start like that. Those atoms were manufactured, then we went from there to galaxies and eventually to stars and etc. Okay, so just have to look at the previous videos to get an idea of what these people are talking about. Okay, I covered a couple people who proposed how the universe came into be, how matter came into be from absolutely nothing. Okay, so that was the deal. Because in the case of Christianity, you have God, making the universe. He's eternal. But in the case of mathematical physics, they get rid of God and they say the universe kind of self-kickstarted. And you say, how did it do that? Please give me an explanation for how matter came into existence by itself and from nothing. Tricky, isn't it? Okay, so this is what these two gentlemen, Stephen Hawking, who's no longer around with us, and Neil Turok, his understudy, I guess. I covered those the other day. Again, I looked at Astronomy Magazine, an article that was written about them where they testified essentially in 1999 about how the universe got started, and that's what we have today. So nothing has changed in 20 years. Okay, and essentially here's the essence of it. In other words, okay, you've got that cone there, which is what you saw a minute ago, the Big Bang expanding, etc., and time goes along the edge of the cone. And the input that Hawking and Turok did put into this picture is that it didn't really start out at a point, okay, at a dot. it started on a little curve there, as you can see on the right-hand side there. There's a little curve, and they call it the P instanton, okay? P because they say this is what it more or less looks like. And instanton is this pseudo quasi-particle from which everything started. And you say, what do you mean by that? How can something start from nothing? And the way they explained it is that time does not go along the edge of the cone. In the case of the instanton, okay, time is merged with space, and both of them go around as a circle all the way down to the bottom of the instanton. Okay? And the instanton is rounded. So no matter how small you make your circle, if that circle represents space and time, you have no origin to space and time because a circle has no beginning or end. It just goes around and around and around in circles like these people did. Okay, so that's their notion. Of course, they don't have a physical interpretation for that. Really, what they do is they say, well, we have a mathematical equation that describes this. And the notion behind it is that there is no beginning to time because it's merged with space, and it's represented by a circle which has no beginning or end. And so those are the notions. That's how they introduce the beginning of the universe from nothing. They call that nothing the instanton, okay? And the reporter asked him, well, where did the instanton come from? And it says, and the answer, that's an irrational question. You can't ask that question. It's unscientific. Okay, so the buck stopped there. Okay, and they said it's just the laws of the universe that created the instanton. So where did the laws come from? They said, well, we don't know how to create something from nothing. That was their answer. So after all that work, we understood nothing. We have no notion of how something can come from nothing. It's just a lot of blah, 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 and mathematical equations, and we have no idea what the mechanism is. Okay, so that's the issue. Okay, here's the another fellow who did not agree with him, does not agree, he's still alive, Andrei Lindy, and he's Russian. He works at Stanford University. He's a teacher there, or a professor. And he said, you know, he doesn't know how to create something from nothing. He thinks that's religion. Sounds to him like religion. No, it's not really religion. What it is an irrational explanation, because you have no way of rationalizing it. You have no way of visualizing the mechanism. That's why it's an irrational explanation. It becomes religion when you believe that that's what happened. When you take that as proof, or to you that's the way things happen, then it becomes a religion, because now you believe that that's how it happened. But as long as you just explain, I mean, I can explain what these people did, doesn't mean I believe in it. I'm just explaining I'm just giving you an irrational explanation. And that's essentially what he's saying. He's saying that sounds a lot like an irrational explanation. What does he propose instead? He proposes the multiverse. He says, well, there are all these universes popping in and out of existence, I guess, like bubbles out there. And that's his version of how the universe started. Ours is just one of the little universes out there that, you know, got kick-started somehow. And again, he doesn't explain it because he doesn't claim to have an explanation of something from nothing. So he eludes that question altogether. Okay, this is just in case for reference, this is Christianity's version, which is God waving his magic wand, according to the Bible, and just saying abracadabra, and the universe came to be. And God is assumed to be eternal. Okay, so God's always been around, so no one created him, and so we have eternity creating the temporal world. Okay, I guess you could say. Okay, so let's proceed here. This is my summary of what these people said. Again, I'm just reviewing this. Okay, the instanton is a pseudo particle. Okay, what is a pseudo particle? Is a concept that is halfway in the process of morphing into a particle. Okay, it's not yet a particle. It's a pseudo, but it's on its way. It's halfway between being, it's in a limbo, somewhere between being and not. That's what they're trying to tell you. Actually, it's an equation. That's all it is, that they treat as a particle. And it's got to do with that word particle, because they use that word, but they don't mean it. They don't mean what we mean in physics by a particle. You mean like a corpuscle, a little grain of sand, a little bead, tiny bead. That's a particle. We understand that. We all understand that. But when they say, look, it's a particle, and you say, oh, what do you mean by a particle? Well, it's an equation. It's a probability function or wave or whatever. Then you start wondering, you're saying, what do you mean? You call that a particle? Why don't you call it a probability wave or whatever, an equation? Just call it an equation. A description, mathematical description. That's what it is. That's not a particle. But that's where they suggest, they insinuate that they're giving you a physical interpretation because they use the word particle. When you dig in there, you find out that the word particle is not what you thought was a particle. Okay. Same with spin, by the way. They use the word spin. They talk about spinning electrons, etc., etc. And you say, okay, I understand all that. Turns out they weren't talking about an electron, and they were not talking about spin, like when you spin a top. No, spin is something else, which they have not been able to define now in countless years. Okay, so spin is not spin. So particles are not particles, spins are not spins. You got to be very careful with the language in quantum mechanics. Okay, the instanton is a solution to an equation. That's what an instanton is. Just a solution. It's a number. Okay, so that's what an instanton is. Okay, how a solution to an equation becomes a particle is a mystery that no one will ever be able to explain in a rational manner. Okay, so this so-called instanton, pseudo or quasi-particle, no, they cannot explain it. They cannot rationalize it. Okay, but you must pray to the instanton because quantum says that it's the God particle. It's not the Higgs, the God particle. The God particle is the instanton because that's from where the universe arose, when it was born. Father Universe was born in that little egg, that little pea called the instanton, okay? Which is an equation. That's all it is, a solution, whatever. Everything started out at the Big Bang, not at the Big Bang, but at the instanton. Big Bang is frame number 2 in the film. That's when the explosion occurs. But before that, frame number 1, these people at least were proposing was the instanton, and that's essentially what all these mathematicians believe. Okay, that they vouch for the instanton because they use this term. Okay, so it's not like nobody believes in this. No, they do, but that's not what they tell the folks out there, because if they say to the common man that everything started from nothing and here's the little pea called the instanton, people are going to say, well, where did the pea come from? And they say, well, you can't ask that question. But it started from nothing. Okay, the whole universe started from nothing. We call it the instanton, but don't ask where the instanton came from. That's more or less the answer. Okay, where all this came from, again, I'm going to go quickly through this. It's just the chronology, mathematical chronology of how these notions came to be. Okay, and I'm going to skip some steps here. I'm just going to say, here was Hamilton, and he invented an incredible concept. Stationary action. Moving while standing still. Okay? Playing baseball while being, fourth, home base or first base or whatever. They have these two notions of motion, static motion, static dynamics, so to speak. It's an oxymoron, stationary action. What do you mean stationary action? No such thing. And the way it's done in mathematics, again, you have to understand this is not the physical notion. They don't care about that. They care about the mathematics of it. And they say if you take the derivative of an itinerary which is short enough, which is in which there is very little to no rate of change, which is what a derivative is. You know, it calculates the rate of change. If there's no rate of change, what you get is zero. So if you throw the ball up in the air and it just stays there for a second until it comes back down, the moment it stays there, okay, you have stationary motion, because all you have to do is take the derivative of that no motion, you could say, and you get a number. It's got to be zero because it's going to come down. There's no rate of change up there. And that's more or less the notion behind stationary action, okay? Try to visualize it as best as you can. It doesn't get any better than that, okay? Okay, from there you get people like Heisenberg, okay, and he came up with his notion of the principle of indeterminacy, or uncertainty principle, whichever one you want. And he said when the ball moves, the ball doesn't stand still, and when the ball stands still, it doesn't move. He had this relation between momentum and position. He says the more you know about one, the less you know about the other. No kidding. Yeah, when I move, I know very little about standing still. And when I'm standing still completely, if I could, you know, completely still, like rigid, like a stone, well, you know, it's very hard to know how much I'm moving. And he got an O for this stuff, okay? And again, it all comes down to this notion of stationary action, of mixing dynamics with static, okay? Why did they have to do all this nonsense? Well, because they couldn't explain action at a distance. So they had to describe it mathematically. And the way you describe it mathematically is, and it has to do with the evolution of quantum mechanics after World War II, which is, you look at the paths and you say, look, there's this motion, okay? But if you take the derivative of that itinerary and there's not enough rate of change in there, then you can say, you know, you have zero as far as your derivative is concerned mathematically. And what that does is allow you to treat that whole thing from a visualization point of view as if nothing moved, okay? Because there's no change in the rate, no rate of change. That's the notion in general, okay? And so one of the guys who picked up on that was Richard Feynman, okay? And what did he do? Well, if you take the classical path integral, you just take a ball going from A to B, and you say, well, it went straight. Okay, we're done, okay? But in quantum, according to quantum, because of the uncertainty principle, the ball, and we're talking about, again, a quantum ball, okay? So keep that in mind. What was a ball? It's an equation. It's a probability wave or a probability function or whatever they want to call it. It's a number, okay? But they're going to treat it as a ball. That's where the trick comes in. And what they do is they have this ball that goes from A to B, but according to quantum, because of the uncertainty principle, that ball goes through every possible itinerary, trajectory that you can imagine. It goes through all of them. It's not that it can go, it's that it does go. A particle goes from A to B through all these itineraries, through all these paths. And you say, okay, let's concede that. I don't know what kind of sense that makes, but is that what you say? Okay, and so what's the deal? And what Feynman supposedly came up with, he said, look, we can treat that also as a single integral. And the way they do that is some of these paths cancel out for different reasons, like, you know, you have destructive interference, okay? You have also, you look at the most relevant paths, again, very selective. They say, well, you know, that one that went throughout the universe, what's the chance, how much does it contribute to our real probability of that particle going from A to B? And they say, well, very little, negligible, infinitesimal, how about nothing? And so they reject those points, those outliers, they just get rid of all that, and they calculate, you know, an integral for that path, and they can come up with what they think is, or what they proposes the wave function, okay, which tells you how particles move in the quantum world essentially. Okay, so this is where his revolution came in, because what's he really doing? He's going to treat all this, and they do to this day, they're going to treat it as a wave, extended wave. It's no longer a concentrated particle until you measure it. But between that, they say, well, it's a wave, it's a field. And what is a wave? What is a field? Well, it's not like a wave is something that travels. They're going to treat it a little differently. They say it's extended. Where is a wave? Where is a field? Well, the field is everywhere. It's the entire universe. But locally here, it vibrates. And they're going to call that a particle. And they're not going to look at whether it's a ball or anything like that. They're just going to describe it mathematically and say, this vibration here, that's what we're concerned with. This is how much the particle is vibrating. Here's the equation. So they represent the equation with a vibration of a fishnet locally, and they say, well, that's your particle. If you can follow my train of thought, that's how essentially what they're trying to do here. Okay, so they have this field, this localized field, which is a particle, but at the same time the field is extended, or the wave is extended, and it's all over the place. And that comes in handy when you want to explain stuff like tunneling, which is another subject I covered the other day. Okay, here is the notion of tunneling. Okay, and the tunneling, what they supposedly saw or observed, they claim they observed in the lab, is that they pass light or an electron from to a barrier. There's a barrier, an energy barrier. Okay, and it turns out that the particle goes right through the energy barrier, is on the other side, and it does so faster than the speed of light. It does so like instantaneously. It appears it's already on the other side of the barrier. And how can that possibly? How can the particle go through a wall? Imagine throwing a basketball, like it's shown there, through a wall, and it's on the other side, but it's on the other side before you even throw it almost. As soon as it touches the wall, it's already on the other side at the same time. That's what these people are saying. And you say, well, that doesn't make much sense. No, it doesn't. And here it is. What they do is they turn the particle into a wave. Or they can turn it into a field as well. They use the wave. And so the wave is already on the other side. The wave is extended. It's already extended on the other side. Okay? So they claim that what they did here is throw a ball, and then they have this extended object that already started at where the ball was, at the starting point of the ball, and it extended to the other side of the energy barrier. So there is no time involved. It's like all you got to do is take an integral there, right? Path integral, and you get a number, and that number is already on both sides. Physically, from their point of view, from the way they analyze this, physically it's already on both sides. So that's how they get through this little story. Okay, that's their story. Okay, and here you have another version of tunneling. Okay, how did they do it? These are the steps. If you want to explain tunneling to someone, very simple. You convert the ball into a wave or a field. That's step number one. Step number two, you tell the crowd that the wave or the field is everywhere. Okay, so now you covered all the bases. The player is at 4 bases at once. In fact, they say that, quantum says a particle can be at all places at once, and it is. It's not that it can, it is at all places at once. And you say, how can that possibly be? They say, well, it's the principle of uncertainty. Heisenberg's principle of uncertainty allows for it. In quantum mechanics, it's the foundation of quantum mechanics. Particle is everywhere. And it's also localized. It's only localized when you measure, when you do something to it, when you try to see it or whatever. But otherwise, it's everywhere. Okay, so this is their explanation. So these are the steps you got to use if you want to explain, tunneling to someone. Okay, step number 3, clarify that each ball tracks its own proper time. Every ball carries its own clock. So if you say, well, how come this particle takes a longer route and arrives at the same time as this one, which went straight? Well, that's to you. See, to the particle, it's carrying its own clock. if it goes at the speed of light or close to the speed of light or whatever, it carries its own clock, and you have time dilation, and that relates it to special relativity. Okay, so that's what they like about it, that you can put all this field theory, this quantum field theory, you can relate it to special relativity, and there's a chance of unifying these two theories. Okay, so this is why they like it also. Okay, you apply the principle of stationary action, moving while standing still or vice versa. And then the ball is now on the other side as a wave or a field in zero time, because the wave is everywhere. Okay? So these are the tricks that they play, and they say, well, mathematically it's sound. In other words, that's what they're going to do. They're going to play with all this stuff mathematically. Okay? And then when they give you the physical interpretation, the physical version, they lost you completely, because that's the part people want to understand, and you won't understand it in the case of quantum mechanics. It's all irrational. Or like Mr. Feynman said, physicists, mathematical physicists, have given up on that. I'm trying to understand all that, trying to explain it or whatever. So they don't deal with that anymore. They consider all that stuff philosophy. That's treated as philosophy. Okay, so let's get to where we are today. Okay, so we have this, the instanton, okay, and you won't find it in it's a particle, right? Pseudo-particle, quasi-particle, okay? And where do you find it in the standard model of particles? Well, you won't find it in there. In fact, there's a whole bunch of pseudo and quasis out there. I call them quasis because they're kind of quasi, okay? And you won't find them you find all these mentioned out there, and people studying them and writing papers in the official literature, but you won't find it in the standard model. So don't look for it in the standard model. You won't find any instanton there, and certainly you won't find a phonon, okay? Okay, and here we have what these particles look like, okay? There's your classical particle. Okay, I think we all understand that. It's a ball. You want it a cube, fine, it's up to you. Triangle or pyramid, whatever. Typically people illustrate it as a ball. What does the quasar or the pseudo particle look like? Well, it looks like that. It's an equation, maybe a wave function. That's the so-called quasi-particle or pseudo-particle. It's a bunch of hieroglyphics, mathematical hieroglyphics. And what does that have to do with a physical interpretation? We're talking about balls going through walls, turning into fields and waves. Well, it doesn't have anything at all to do with that. The way they do it is they simply say, look, this is the equation, this is the description, and that's what they care about. Okay. Here's the definition, I guess you could say. Quasi-particle and collective excitations, that's what they are, okay? They are emergent phenomena. Emergent phenomena. What is an emergent phenomena? I've got a little definition here. Give me a second here. Let me get it up there. Here it is. Okay, here's the definition of what they call emergence or emergent phenomena. For those who are not familiar with this concept, it occurs when an entity is observed to have properties. Properties. They're going to talk about properties, okay, not the entity itself. Its parts do not have on their own properties or behaviors which emerge. That's why it's called emergent. Only when the parts interact in a wider whole. Okay. So that's the notion of the quasi-particle. It's a collective excitation, which is, again, an emergent phenomena that occur when microscopically complicated system, such as a solid, okay, behaves as if it contained different weakly interacting particles in vacuum. Okay? And here's an example. An electron travels through a semiconductor. Its motion is disturbed in a complex way by its interactions with other electrons and with atomic nuclei. The electron behaves as though it has a different effective mass, traveling unperturbed in vacuum. Such an electron is called an electron quasi particle. Okay, so see they have all these emergent properties, and what they're going to do is they're going to treat them as actual particles. So they're not going to talk about the particle anymore. They're going to talk about these properties that emerge when you have a collective vibration or whatever of many electrons, many particles, many atoms, whatever. When they look at the whole thing, they say, oh, a new property emerged. And they're going to call that property a pseudo or quasi-particle. Okay, you see how they morph the language. Essentially, you know, what they did was take a concept such as a property of an object, and that's what they're going to treat as a ball, as a particle, as a corpuscle. And they're going to do that throughout their physical interpretation. When you ask them, when you finally put them against the wall and say, hold it, are you talking about particles? Oh, no. In quantum, there are no such thing as classical particles. What we're talking about here is, equations. That's the answer you get. Okay, so what's the deal with a phonon? Well, the phonon is also one of these pseudo-quasis. Okay? And again, they had to create these little particles to explain certain motions of many particles or many electrons or many atoms at the same time. In the case of the phonon, you say, well, why can't we use the same, one we use for tunneling or for some of these other things, like why can't we use the instanton there? Why can't we use the same particle all over and over and over? Well, they had to categorize all these particles. And in the case of the phonon, this is the particle of sound. Yeah, you heard right. It's the particle of sound. You wouldn't be able to hear if it weren't for the phonon, okay? You say, hold it, what do you mean sound? Well, again, it's a quasi, it's a pseudo, means that they're going to look at the excitation of many particles, in this case, in a crystal lattice. Okay, so you've got all these atoms that form a crystal lattice, say of a metal or any solid, for example. And they're going to vibrate, okay? And that vibration creates a sound. They're going to call that collective sound a particle called a phonon. Okay? Yeah, you follow me? This is what they're going to do here, okay? So here's the fellow who invented it. His name is Igor Tamm. He's a Soviet scientist, died already. I think that's him because it's the only Igor I could find. I guess he moonlighted in a Frankenstein movie, and so there's your Igor. The concept of phonons was introduced in 1932. Look how far back, okay? By Soviet physicist Igor Tamm, okay? The name phonon comes from the Greek word which translates to sound or voice, because long wavelength, listen to this, long wavelength phonons give rise to sound. So when we have a long wavelength of a phonon, which is what? An excitation of many particles, vibrations, they're going to say that that whole thing is a phonon, and without phonons we would not have sound. Okay, so now the excitations, the properties of objects have suddenly become a phonon, and they're going to treat that as a particle, and they say, well, without phonons you wouldn't be able to hear. So this is where the metamorphosis occurs, where the concept suddenly becomes something that hits your ears or whatever, vibrates in there in your eardrum, something like that. You try to imagine it if you can. The name is analogous to the word photon. Okay, so you have phonon, photon. Okay, see how they came up with all this stuff? A phonon is a collective, okay, many, excitation in a periodic elastic arrangement of atoms or molecules in condensed matter, specifically in solids and some liquids, often referred to as quasi-particle. Okay, why do they refer to it as a particle at all? Why do they use the word particle if it's not a particle? Is it to confuse you, so that you think in classical terms, in classical corpuscles? Is that the point of using the word particle, to sneak it in there? I mean, what is this standard model of particles? Are we talking about, is the glue on a particle, is the mu on a particle, is the electron a particle? Or are these just equations? What is the standard model of particles of quantum mechanics? So they use the word particle, which they inherited from classical mechanics. They kept using it because they suggest or insinuate that they're going to be dealing with little balls when they're not. They're going to be dealing exclusively with abstractions, with equations, which they, when they give their physical interpretation, they're going to morph into particles. They're going to insinuate to you who don't care about the math. You say, okay, give me the bottom line. I want to know how this particle got over there, what the trajectory is, what it did, how it collided. And they're going to say, well, yeah, it's that's when we treat it as a ball. So here they're colliding these things, like in the CERN at the Large Hadron Collider. And they're telling you they're colliding, they're smashing, they use these words, right? Smashing particles. And you say, okay, I understand that. No, you don't, because they're striking equations against each other. And the pi goes this way and the rho goes that way. A phonon is a collective excitation in a periodic, etc., okay, often referred to as a quasi-particle. It is an excited state in the quantum mechanical quantization of the modes of vibrations for elastic structures of interacting particles. Phonons can be thought of as what? Quantized sound waves. Well, there is no physical object called wave. Wave is also a verb. And again, if you look at that transverse wave that they always put since the days of James Maxwell, it's all vectors, mathematical vectors, magnitude and direction. That's all they are. And they put all these vectors moving on the screen. It's very scary stuff, okay? So that's what they are. They're quantized sound waves similar to photons as quantized light waves. Okay, so this is what they do. They reify all these objects. And what did we see at the beginning? That anytime you do a reification of a concept into an object, treat it as an object, well, you're doing some terrible irrationality in the discipline known as physics. Okay, here so that you can see what they how they illustrate this stuff. Okay, and here you see a visualization of the phonon. Okay, but the phonon is not one of those particles or anything like that. It's what you're seeing, the effect, the excitation, all these of the collective of the whole neighborhood of particles, right? That whole thing is called a phonon. And you would not be able to hear if it weren't for the phonon, what? Particle. So they turn all that concept into a particle, and now they deal with a particle because that's how they do it in mathematics. They get a solution, they say, okay, this solution we're going to call phonon. And now they're going to move that solution around to give you a physical interpretation for what they're talking about. So these are different modes of vibrations that that they came up with, and each one of those different vibrations is known as a phonon. So you got phonon 1, phonon 2, phonon 3, all these different phonons. Okay, great stuff. Okay, so it's fancy stuff. They like to look at these little pictures and illustrate them. They call these collective vibrations phonons. Okay, so that's what you're getting for the money you pay these guys. Okay, that's what they're doing here for you. Okay, let me get this one. Here's another version of this, okay, more or less, so that you can see it. And again, an explanation. Vibrations of atoms in a solid can be treated as elastic, acoustic waves propagating through the lattice. Okay, so you have a lattice, and lattice is like the side of a, or one of the lines that connects two atoms in a crystal. Okay, so you go in there with your telescope, microscope, whatever, you see at the atomic level, well, then what you've got is one atom here, another one there, and somehow that forms a lattice, forms the edge of the crystal structure. And what they're going to do is going to tell you about the vibrations that happen all along this at the subatomic scale. Okay, so the energy of these waves are quantized. Okay, they're turned into a little ball. Okay, that's what quantized means. Quantum, little ball, packet. Okay, because the atoms are discrete quantum particles. Quotation. Okay, phonons are discrete packets of vibrating energy. Okay, and there you see it. You say, what is the phonon? The little ball that's going up and down? No, the phonon is the effect, is the motion of all those particles. That motion, that vibration, that's what's called a phonon. Okay? So now you know what a phonon is. You wouldn't be able to hear if it weren't for all them phonon particles hitting your eyes, all those vibrations. Okay, and so what is energy? They say energy, here it is. This is what Nobel Prize Feynman told us about energy. It is important to realize in physics today we have no knowledge of what energy is. Yeah, because energy is not a what. Energy is a concept, and so you can't say what is energy. No, things we point to and concepts we define, and he never realized that. Okay, never was taught that in wherever he went to school. Okay. Okay, and because of this, you get to the next level where you get people talking about types of phonons, like talking about types of shirts or types of pants. Well, here's one fellow who talks about different types of phonons. Optical phonons are excited easily by light. In acoustic phonons, both positive and negative ions swing together. Okay, so there's a physical or pictorial representation of an acoustical mode. How about the optical mode? Well, optical phonons, positive and negative phonons, swing against each other. Okay, so they have all these different categories of phonons, which are simply different modes of vibrations. Okay, so they get to the next level where they start treating phonons not only as particles, as discrete particles, but they began to move them around, categorize them, and do all these fancy things with them. What are the questions you should think about today after listening to all that? Well, these are the questions that I propose to you for you to ponder. Okay, what is a particle? That's the first question. What is a particle? Is a particle, like these people say, a pseudo, a quasi? Or a particle is the corpuscle of old, of the ancient world, of the classical world. Is that a particle? I mean, when someone says particle to you, what are you thinking of? Are you thinking of an equation, or are you thinking of a speck of dust, a grain of sand, a little p instanton, a p? You know, what are you thinking of? Well, everybody thinks a particle is a particle, you know, like the little particle that's in your eye. Oh, I got a particle in my eye. That's what people think of the word particle. At least that's my take. I don't know what yours. You might think particle is, you know, an angel, a spirit. I don't know. So, first question, what is a particle? Okay, second one, does an excitation qualify as a particle? So you have a vibration of whatever. Could be water. Could be the air, for all I care. You have a vibration of something. So that you have a something, you have a bunch of atoms there, they're vibrating. Is the vibration itself, does that qualify as a particle? Can you say that the vibration is a particle, which is what they're doing with pseudos and quasis? Okay, is a pseudo quasi particle a particle? Okay, so this is the train of thought. This is my reasoning behind this. I mean, can we treat all this as particles? Are these real particles? Can we talk sensibly by converting vibrations into particles? Vibrations of what? Of energy, which is even worse because you have vibration of a concept. Like saying, oh, we have the vibration of intelligence, we have the vibration of love, and that's a particle? If quantum particles are not objects, things, right? If they are mere concepts, does quantum mechanics have anything at all to do with physics? Okay? What is physics? Is physics about giving you physical interpretations? I mean, these people are just going to give me equations, and which are descriptions, and they're going to say, well, we were able to describe something in the lab. Yeah, you were able to describe it, but you know, you're not able to explain it. You can't tell me what's happening in that little world. And one of the problems that comes up with this is what I mentioned the other day, and that's that when you have light interacting with atoms, like with electrons, well, you can say that light and even the electron belong to the quantum world, and we don't know exactly what happens there. We cannot explain it. Fine. But when it interacts with atoms, the real world, like light hitting your table, well, you have to explain that interaction. Now you're not talking about the quantum world. You're talking about the interface between the quantum world, the one they can't explain, with the real world, which is the one you see, touch, measure, etc. So now you had a problem because now you have to explain that interaction between the real world and this quantum world which they've invented. Okay? And that's where they run into trouble because they cannot explain that interaction. Okay, so let's move on. We're going to do a little bit of questioning and answering. See some of the comments people made, some of the questions people asked. Okay, so let's go with that. One fellow, okay, he's been following some of these things for a while now. Put him on the other side. Let me get him up here. Okay, he says, square is not an object. Keeps insisting. Well, until you define what the word object means, we have no idea what you're talking about. See, here we define words, and here I defined it. Okay, here it is. Okay, what is an object? Okay, object is that which has shape. Okay, and there's a square, is that thing in red, and does that have shape? And I would say that even a baby or a kindergartner would tell you, yeah, that has shape. What kind of shape? Well, it's got squarish shape. Good. That's all we need. That's the only condition that we needed to make it an object. And so until you define the word object, we have no idea what you're talking about. You need to define the word object. Okay? Otherwise, you're just spinning your wheels. And yeah, a lot of people do a lot of that. Let me get these out of here. Okay, next question here we have, or one fellow says that he's got a better definition than me for the word object. Okay, great, love it. I have a better definition. Object, that which has form and location. Okay, a tribar has shape, though can't be real. Notice the words that he uses. A tribar triangle has shape. A tribar triangle can't exist. Therefore, not all shapes can exist. Objects that exist for the purposes of physics must have location, or else we can be talking about a 2D drawing. So he's not talking about the word object. He's talking about existence. And so here's the homework for him, if he wants to take it as homework. Object, that which has shape. If it has location, we're talking about something else. We're talking about existence, according to rational science. Exists, that which has shape and location. Okay? So if he's going to say that an object is the same thing as existence, well then tell me what exist means. Tell me, define the word exist. Define the word existence. Otherwise you have no difference between exist and object, and that's the same problem that David Hume and Immanuel Kant had, that they couldn't distinguish between, and everybody that came after, right? Just singling them out. No one could ever tell the difference between an object and an object that exists. And so we have to distinguish the word exist from the word object. Okay? That's where the problem is. Okay, let's see if we can get rid of this one. Okay, next issue, next comment. Fellow says, let me get this here. If we are going to talk about physics, there is an actual dictionary we are using. The most popular one is a Dictionary of Physics 6th edition. He said that a couple weeks ago. Okay, that's where his discussion started. Okay, so what came next? Well, this is what came after that. I guess was the last week or whatever. Physics definition of object. Okay, so he says he took this out of a scientific dictionary. He says identifiable collection of matter, which may be constrained by an identifiable boundary. Okay, that was his definition. He says he pulled that out of a dictionary, a scientific dictionary. Okay, when you look it up, you don't find it in a scientific dictionary. You find it in the Wikipedia. See? And but he says you can simply Google physics definitions. Okay, and an object has to be three-dimensional. He says a rock is an object that doesn't experience existing. A circle, square, triangle are non-objects or concepts. We call them geometry, blah, blah, blah. Shadow is a two-dimensional geometry. All those are examples. Okay, so far we don't have a definition that he can defend, because you got to defend your definition even if you took it out of a scientific dictionary. It turns out that, when you look it up, you find out that he got this not from a scientific dictionary. He got it from the Wikipedia, because there you see it, an identifiable collection of matter. And let me put his definition again in here, see if I can find it. Okay, identifiable collection of matter. Where did he get that? He got it from the Wikipedia. He didn't get it from a scientific dictionary. And then none of the other ones that he gave are definitions. They were all examples. Okay, and when Googling the definition of object for physics, we find, again, you find the one in the Wikipedia, you find one that you'll find in Hub Pages. You see there the link. And if you go there, it's the same definition I have, essentially, what this fellow put in there. And object, then you have Bozeman Science, another one that's you'll find on the in YouTube. There's the link. And it's an object, anything that has no internal structure. Okay? So that's what he put. But again, he could not, this fellow could not defend his definition. Okay, and so what does this fellow reply to that? He says, Wikipedia, the definition of object doesn't originate from there. Well, I don't care where it originates. I think you got it from there. I don't think you got it from a scientific dictionary, because, again, you cannot put a link. And he says, YouTube isn't letting me post links, so you have to do your own search. Well, you can put a link. You just have to spread it out. I mean, I put links, and I have no problem putting links in other people's places, but assuming you do, no problem. Just separate it like that. Separate the H from the TTPS, and you can put the link. We'll figure it out. Now, if you couldn't do that, well, I guess you're not smart enough, okay? And so he says, it's definition of object, that which has shape that is irrational. Well, you have to define what irrational means. See, we define irrational here so we can tell you whether you're irrational or not. If you're going to accuse someone of being irrational, well, you got to define irrational. And if you can't do that, you said nothing. Okay? And then he continues, it says, the first priority in the physics definition of objects is that it is three-dimensional. Well, until you define the word object, we will not know. Okay, we will not understand what you're talking about. And a collection of matter, you haven't said anything, because we don't know if that's three-dimensional, two-dimensional, non-dimensional. Okay, you have these people in quantum, they consider that matter is made of nothing. So whatever you said by collection of matter, we have no idea. Again, you got to defend these definitions. It's easy to copy, just copy from the Wikipedia and put it in there and say, oh, this is the scientific definition. Well, even if it were so, please defend it. Okay? And we do attack that definition, and I've attacked it several times. You got to address the issues that I raise against it. If you can't address them, all you're doing is putting your tail between your legs and running away. You're eluding the questions. And we attack the bull by the horns. We don't escape anyone who wants to challenge the definition of the word object. Hey, we'll tackle you, no problem. Okay, shape is the only universal property that all objects have. There is no other universal property. And again, he who doesn't like it only has to define the word object. Then he can begin his defense. Okay? He's got to defend his definition. Okay, another fellow, he says the following. He says, the something from nothing and vice versa, irrationality of the mainstream exists in Bill's hypothesis as well. Oh, okay, let's find out. Bill's threads must bend to form ropes and atom. Okay, for a one-piece 3D thread to bend, it must stretch and compress. Okay, to stretch it must create new matter, and to compress it must destroy existing matter. A one-piece rod, tell us how it could bend without distorting itself. Okay. Okay, first let's show that, okay? Here's a rubber band, and I stretch it, I bend it. Did I create new matter? Okay, so here it is. I'm stretching, I'm doing whatever I want with it. Did I create new matter? Okay, so that's the first thing you should keep in mind, see if that makes sense to you. But it turns out someone answered for me. You beat me to it, kind of. And the fellow says the following. This is another fellow who answered. If I can get this thing in there. Okay, let me put it over here. Fellow says the following. He answered, this first fellow. He said, the thread is a single object and it bends. You don't need to do anything, any creating or destroying of matter. And again, I showed that with the rubber band. We're not creating new matter and we're doing everything we want with it. You can do that with water also. You can move it all around. You're not creating any matter. You're just moving atoms around. You are just confusing a fundamental continuous object with an object made of smaller parts that move closer to each other or create gaps between them. You saying part of the thread can curve into itself. This is you thinking the thread has parts that can curve into itself. Okay? So yeah, those are all very good topics or answers that fellow gave him there. But let's go a little further here. Okay, let's show where the problem is in reasoning of the first fellow. Okay? And so let's go step by step. Here we have a rubber band. Okay, and we stretch it. Okay, so we stretch the rubber band, kind of like what I did just now. Okay, you're going to stretch it there. Okay, we're going to do that. We created no new matter. Okay, first of all. Okay. But what is he saying? He's saying, well, and there you have the curved rubber band, same thing, okay, which is what he said. One part, okay, and here I'll show it in more magnification so that you see what this guy was referring to, okay. And he says the following. He says, looks like this, like, you know, the inside is compressed, the outside is extended. That's what he was talking about. And no, you don't have to create new matter in our real world in a rubber band, for example, but he's raised an important issue. Let's face it. He says, look, but if you say that the thread, the universal thread that underlies all matter, is made of a single piece, then now we have a different situation, because in the case of a rubber band, what you have is the atoms are kind of getting farther, which is what this other fellow answered. They're getting farther away from each other and closer, depending on, you know, the angle and so on. Okay, so we're dealing with the same atoms, but they're just stretching or getting farther away or whatever, whichever way you want to explain that in the micro world. Okay, but in the case of the thread, this fellow's right. If you're going to bend that and it's made of a single piece, if you bend that, you're creating matter from the void. Okay. Because the top part is going to be extended, the bottom part is compressed, and if it's not made of little pieces, then in the top part at least you seem to have created matter, or maybe you could even argue that the matter from the bottom somehow shifted to the top, which again means that it's made of parts. Okay, and that's not made of a single piece, because if it's made of a single piece, you would think, right? You would think that the bottom compressed matter out of existence, the top part extended and created matter from space, from vacuum, from nothing. Okay, so that's his argument. Okay, so let's understand the argument first. Okay, so let's look at how we're going to answer that. Okay, I think it's an important issue to answer. Okay, and here's a rubber band. Rubber band is made of atoms. So here you have this rubber band again, and in there it looks like that. There's got gazillions of atoms in there, and they move around, etc. They get farther away, closer to each other. Okay, that's how a rubber band is. So let's go step by step here. Okay, and here Here under the rope model, you can see how we do that even in the world of atoms. Okay, so far we're still in the world of atoms here. Okay, we have the rope hypothesis. Atoms are made of threads, the same threads that make the rope, and that create the distance between them because the atoms slide along the ropes. Okay, and so the threads, when they get to the atom, they open up, they form part of the atom momentarily as the atom slides towards another or gets farther away. So the atom is sliding along the ropes, okay? And the threads are absorbed and then released. Absorbed in the front, released in the back, you could say, okay? So the ropes essentially, or the threads, the two threads that form the rope essentially slide over our atom as the atom moves towards another. That's the notion, that's the theory, okay? That's how we're going to explain that, okay? But again, here we're talking about parts. And this fellow's saying if you have a single piece, how are you going to explain bending? You got to create new matter. And down here, you know, where you have shorter distance, you have compressed matter out of existence because it's a single piece. Okay? It's not made of parts. You got to keep that in mind, okay? It's very hard to keep that in mind. Sometimes people lose track of that. So this guy's on the right track there, okay? Okay, here we have two situations. And I can't think of a third one, okay? And I'm going to put that as questionnaire at the end, okay? Here you have a single piece thread, and you have a segmented thread made of discrete particles, okay? Now I can't think of a third option. It's either made of a single piece or it's segmented, made of discrete particles. I don't think there's a third category, but that's for smarter people than me to come up with. Okay, so that's the starting point. But this guy is saying if it's made out of a single piece, it can't bend because otherwise you're creating matter from the void. So does that mean that it's going to be segmented? Is that what he's proposing in the alternative? And if not, what's the third option? Okay, that's where we're at. Okay, we understand that? Either you make it of a single piece and you're going to bend it without creating new matter, or you do particles. You do kind of like the quantum thing. You're going to have all these discrete particles, okay, that make up the thread if you're going to propose the thread, okay? Because you got to explain how the thread bends and so on without creating matter, new matter. Okay, so where's the problem? Well, I say that you create many more problems with the bottom scenario than you do with the top. Here's the bottom scenario, okay? You have all these particles, and you can explain light on light. You can explain how one thread goes through another, or ropes if you want, and it doesn't matter. How one object goes through another if it's made of particles, discrete particles, because all you do, what they have in their minds is that the spacing between two particles is what goes through the spacing between two other particles. For some reason, you know, the red balls don't collide against the yellow balls. They just happen to match in such a way that space goes through space. That's how they're going to explain this, I suppose, because otherwise, you know, they have to explain this. You know, I cannot imagine it in any other way, that what they're talking about is space going through space, gap going through gap, okay? But we created a monster here. A bigger monster than the one that I'm proposing, made of a single piece, because what? Here we have this situation, you know, I want to go step by step so that people understand what the issues are, okay? These are the problems, okay? And I call it the principle of single piece, okay? In our macro world, we have no entity that is made of a single piece. There's nothing you can come to me from a hardware store, from a food store, from anything that you can imagine. Air, water, liquids, gases, whatever comes to your mind, we have nothing that is made of a single piece. No physical object that is made of a single piece. Okay? So everyday matter is made of parts, atoms. Okay? Therefore, we have no object in our everyday experience to compare Mother Nature's continuous thread against. So if Mother Nature has a single thread there with which she does everything, it's made of a single piece, we would have no way in our real world to imitate that. I could not be able to imitate it, for example, with this. I can say that the shape of the thread is like this, and that's about where the analogy ends, but I cannot say that the thread is, for example, like a rubber band or a string, a closed loop string or whatever. Because all this is made out of parts, made out of segments, out of individual atoms. And so, and according to the rope model, it stretches because, again, the atoms slide back and forth while maintaining this tension. Okay? So we have nothing in our real world with which to mimic Mother Nature's single thread made of a single piece, if that's what she has out there, because we have nothing in our universe, in our macro world, with which we can imitate or simulate that single piece thread, which is malleable. And the malleable part we can set aside, but we have no way of simulating single piece because we have nothing that is made of a single piece in our real world. Okay, so we have no object with which we can simulate light or gravity or magnetism. And here's the two corollaries. There is no evidence that single piece is equal to rigid in our macro world. Because even when you take a steel beam, just to mention one item that we typically associate with rigidity, if you take a steel beam, you can stand on it, jump on it. Yeah, there is motion in there. We don't notice that, but yeah, there is motion in the molecules and the atoms in there. But that's what we call rigid. We say the steel beam is rigid, but that steel beam is made of parts, and we call it rigid. So the rigidity of our world cannot be extrapolated to the rigidity of Mother Nature's world, or vice versa. You cannot extrapolate the malleability, meaning that it's made of parts, to Mother Nature's world, where she has a single thread, which is malleable, but it's made of a single piece, because we have no way of simulating that. Not with anything that we know of in our real world, in our macro world. Okay? Corollary number 2, experiments will not tell you what light is. Again, because, and here are the questions. Let me get to the questions so that you know what the homework is. If you really want to challenge what I just said, here it is. Here are the questions. Okay, let me get it down here. Issues to be resolved. Is there a third option beyond continuous or discrete/segmented? So for those who propose the thread, you have to determine whether it's segmented, made of parts, or a single piece. There is no, as far as I know, there is no third option. But if there is a third option, someone smarter than me, hey, come up and show me what it is. Okay? As far as I'm concerned, it's either continuous or segmented. There is no third option. So if you have a third one, let me know. Does light go through light? And let me do a little experiment. People like experiments. Let me remove this for a second here. Okay. I'll do a little experiment just to show you. Do it this way. I've got this light. Got to press. Okay, there it is. Okay, that's light. Yeah, I go out of focus. And here's another light. Okay. Okay, so I have two lights. And I'm going to run them right through each other. Okay. Does light go through light? Yes or no? Okay. So here we have light going through light as far as I'm concerned. Okay. So what's the next question? Or what's the next issue? Let's get that back in here. Light, as far as I'm concerned, goes through light, so you got to answer that question. Does light go through light? You got to go into these steps, okay? Is the mediator of light an object or a concept? If it's an object, we have the definition of object, that which has shape. Otherwise, you got to define what an object is, if you don't like that definition. So if it's an object, it has shape, and light goes through light, and light is mediated by an object, you have to explain how Mother Nature does that trick. How does light go through light? And yeah, you won't find anything in our world any macro object that goes through another macro world object. Because if you take, I don't know, a string and you run it through another string, or I can do it here with rubber bands, okay? They don't go through each other. They hit each other away, okay? They can't occupy the same space. So if light goes through light, as I just showed, unless you have a different explanation or a different description or assumption or whatever, if light goes through light, and if light is mediated by an object, what is an object? That which has shape, unless you have a different definition that you can defend, then we have to assume that this object that Mother Nature uses as a mediator for light goes through the other object that Mother Nature uses to mediate light. We have two lights, one going through each other. They're both objects, they both have shape, and one goes right through the other. And there is no other way to explain it other than that you have a continuous entity that has the property, the attribute, the characteristic that it can go through itself. We don't have anything like that in our macro world, but you have to explain light on light. You have to explain gravity on gravity. You know, the moon, is that a good example? We can use almost any example there. We have Jupiter is tied somehow, you know, gravitationally to the sun. And it turns out that sometimes the path of that gravity interferes with that of the Earth and the Moon with respect to the sun. So the gravitational attractions kind of mix or interfere with each other when they're aligned more or less on the same axis. And so gravity goes through gravity also, because Jupiter doesn't care if the Earth gets in the way. It does in the sense that the Earth adds to the gravitational attraction at that moment in time, but it's not like because the Earth got in the way, Jupiter flies away or Pluto flies away. No, it's like, it just, if anything, it just adds. It's like gravity goes right through the Earth for Pluto. The gravitational attraction of Pluto to the sun goes right through the Earth, whether the Earth is there or not. The only thing the Earth does is add to the gravitational attraction. It doesn't interrupt it and Pluto flies away. You understand what I'm saying? So light on light, gravity on gravity, magnetism on magnetism, you got to explain that. You got to explain these things. How you can pass your hand right through magnetism. Is magnetism mediated by a physical object, meaning that which has shape? If I can run my hand right through two magnets, when they're pulling at each other, you know, you feel the tension there, and I can run my hand right through it without any problem. Nothing stops my hand. And so, is magnetism mediated by an object? Yes or no? And if you say no, well, then what is it mediated by? By what? You know, what is this magnetism stuff that's in there? Is it an object? Does it have shape or not? Whether we can see it or not, or touch it or not. That's the question you got to answer in physics, okay? And so, is the mediator of light an object or a concept? And again, you can't use concepts, because concepts, you can't move concepts around. You can't use them in physics to say energy did this and a field did that and ether did the other thing. You can't use concepts as mediators, which is what everybody out there and their mothers do even to this day. If the mediator of light is discrete, okay, the quantum ether, okay, well, I wanted to say really, is the mediator of light discrete? Okay. Again, is it segmented? Okay? And then if it's segmented, well, how does one particle or whatever segment pull on another, affect another if they're separated by space? How does the particle influence another particle? Whether push or pull, remember, because why would it be moving in that direction? And if it does move in that direction, why do they affect the one on the other end? So particles have a problem because you have no way of showing physically, of imagining or visualizing how a particle affects another from a distance. And they're separated by space. I don't care I'll just magnify it as much as possible to show that they're a mile away from each other. As long as they're not touching, you have no way of showing how one particle affects another, especially pull. How does one particle pull on another? And that's the problem with quantum mechanics and all of mathematical physics. They cannot explain the force of pull because they never discovered elongated entities. Invisible, intangible, elongated entities. Okay? If the thread is segmented, how does each segment influence its neighbor? So those are the questions for anyone who wants to tackle the problem. Okay, so it's easy to talk and say, Bill, you can't explain how matter is created. We don't create matter by bending the thread, because the thread is like this rubber band in the sense that it doesn't have to create matter from the void. It just has the ability to be flexible, even though it's made of a single piece, which people typically associate with rigidity in our world. But it turns out that the rigidity of our macro world is made of parts, and it's not rigid. You take the most rigid stuff that you can think of, and it's moving. It's not rigid. Okay, so we don't have rigidity or single piece in our universe, in our macro world. And so, until you get your brain around the fact that, Mother Nature has a single piece malleable entity, you're going to have trouble. You're going to have trouble understanding how Mother Nature does her tricks. Okay, a couple more issues here. There were several. Well, it says, so what is your explanation for why light slows down in a transparent medium? Well, the explanation is that, light never slows down. Okay? Light always travels at little c, at 300,000 kilometers per second, and light consists of torsions. Okay? 3D wave propagating along a DNA-like medium that interconnects any two atoms. And so how do we explain so-called change of velocity, which is what quantum says happens? Well, here we do it with a prism, and we show the differences between mathematical physics and what we propose. Here we have it. Okay, you have if you do it with waves and you do it with particles, what you have is one-way mechanisms. They all travel in one way. And what we're saying is there's no traveling. The ropes are already connected from every atom in the universe to all atoms in the universe. So all we have is locally, in this case, we have torsion coming in, white light, and what the prism does, too lengthy to explain all the details here, but what the prism does is break it up into different wavelengths and frequencies. What is wavelength and frequency? Well, what you're talking about is link lengths. The links that make up the rope. Either they're elongated or short. Okay, either you have short links or long links. And there you have the equation. The wave equation is the equation of a rope. What we're saying is that when the links are long, you have fewer links. And when you have many links, the the lengths of links are short. That's what we're saying. Okay, and that's why we have colors. Colors are simply different link lengths of the rope. Okay, so it's a different model altogether. Do you believe in the model? We don't care. We don't care. We explain the model so that you understand it. You reach your own conclusions in your own dark basement. Okay? This is not Sunday school. This is physics. We explain. We give you a mechanism that you can sink your teeth into. You can compare, and then you reach your own conclusion. That's the way science should work. Not the way it is now, where people talk about proof and evidence and prediction and experiments and observation. I'm going to get to that in a second. Okay, here's another fellow who puts a comment, says, the concept of ether, in my opinion, can be extended to the rope hypothesis. Oh my God. If the whole is a single thread, then it has shape. Consequently, if we consider part of it in any zone or region of the universe, without void or of course, universe plus zero equals universe, okay, which does not form an atom of hydrogen, for example, then the threads and ropes can be called ether. Oh my God. Okay, let's address this gentleman. Here's my answer to that. Okay, put it side by side so we... Okay, so why don't we just call it the ether? Okay, that's what he's saying. I guess he can't tell the difference between a bunch of particles, which is what the ether is and has always been since the days of the Greeks. And anyone who talks about the ether usually doesn't have the slightest clue what the ether is. They never defined it. They can never tell you exactly what it means, and there are different notions of what the ether is, whether the ether fills space or is space. And those are two different notions. Either space is a container that contains all these particles that wave and create the electromagnetic wave, or the ether is space, and then in which case you got to tell me what's outside of that ether. Or does the ether stop somewhere? Okay, do those particles stop somewhere? And again, you can see there's a difference between the single thread and the ether. But why don't we call the single thread God? How's that? Some people have proposed that, and they say, oh, that's God. Well, is the guy on the left the same as the guy on the right? I mean, is the thread the same thing as a fellow who creates the universe? Okay. Or why don't we call it space-time? I mean, that's a good way of calling the thread. We won't call it the single thread anymore. We'll just call it space-time. They're equivalent, aren't they? I mean, are those two things equivalent, the guy on the left and the guy on the right? So what these people do is they don't want to release the words that they learned at the monastery. Okay? They learned this word ether, and they've been brainwashed by the word ether, and they don't want to let go of it. Like the Christian doesn't want to let go of God, and the relativist doesn't want to let go of space-time. They say, no, I was born with space-time, I grew up with space-time, everything is space-time. And now they see the thread and they say, well, there's a different interpretation. We could call that space-time also. See, because the thread has locations, got length, width, and height, and we have time, and so we have four-dimensional thread. They can go on and on forever. It's like it happened to me with some Muslims, and they were looking at the Quran, and they said, look, the Quran mentions your rope. I said, what? What? Yeah, you didn't come up with anything new. See, the Quran, they found the word rope in some lost paragraph, some verse of the Quran, and they said, see, here's the word rope. So God already had come up with a rope. He didn't invent anything. Yeah, the Quran already had it. Muhammad already figured it out. And again, you can take that as far as you want. I mean, you can say the ether is the rope. You can say space-time is the rope. You can say God is the rope. It's nonsense. Ether means bunch of particles. And anyone who doesn't like that definition just has to define the word ether. That's how simple it is. And I'm sure I'm going to be able to tear you to pieces. So please do not define ether in any other way except bunch of particles, because it means that you have no clue whatsoever. Okay? So the word ether has to be defined. In fact, I put up 10 videos the other day, so go through them so you can see my criticisms of the ether. No one knows what the ether is. Anyone using the word ether, obviously as to prop up their theory, has no clue what the ether means, because ether means bunch of particles. And there's a lot of problems with the notion of bunch of particles. Okay, final issue. There's two. Well, here's one. Next to the last. And so this fellow says, how is it possible to do science without some observation? How can we explain gravity if nobody is there to see the apple fall? Oh my God. Okay, let's answer that question, because lots of people have that. What do you mean, Bill, that observation is not part of the scientific method? No, observation has nothing to do with science. We do not gawk in science. You can gawk all day and not understand anything. You're not able to explain anything. So observation is not part of the scientific method. So let's go through the steps so you can put it in the proper context. The problem here is context. Let's go through the context, okay? Here it is. The definition of science. Let's begin there. What is science? Rational explanations. Where in there do you see the word observation? It says explanation, not observation, not prediction, not description. It says explanation. So there is no provision for observation in the definition of the word science. If you don't like my definition, hey, you got a single recourse, and that's define the word science in a way that you can defend it. Don't copy it from the book, because for sure you're going to get it wrong. There's not a single book on planet Earth that has a definition of the word science. So whatever they taught you in high school, it's for sure irrational. And I'm going to really beat you up on that. So you better be prepared to defend your definition. Don't just copy and paste. Okay, and you can see observation is not equal to science. Okay, did Hawking ever observe, Stephen Hawking, right? Did he ever observe a black hole? He was the king of black holes, right? And did he ever observe a black hole? Do you need to observe a black hole? Do you need to observe a photon? Do you need to observe an atom in order to talk about it, in order to use it as an assumption in a theory? And what does observe mean in the religion of mathematical physics? It means proof. Observe means I'm going to shove it down your throat. I have evidence. I've observed it. What the guy is doing is testifying. He's serving as a witness. That's how it's the word observe, observation. These words are used in mathematical physics, so-called science. They are testifying. They say, I observed. And if you say you observed, then how can you challenge that if the guy's telling you that he saw it with his 2 eyes? What did he see? Light? Did he see gravity? Did he see the mediator of magnetism? No, he did not see. He did not observe like with the 2 eyes. And so when you look up the definition of observation or observe, well, then it gets a little tricky, because they don't mean observe like with the 2 eyes. Okay, what they observe, if anything, is the visible stuff, not the invisible stuff. So mathematical physics is 100% observation, meaning experiment and persuasion. What they're trying to do is shove down your throat a theory saying they proved it. That's what the word observe means. But they cannot observe the invisible. They can only observe the visible. And then the rest they interpret and they pass it off to you as an observation. No experiment is ever going to tell you what light, gravity is. In other words, the only way to look at these things is to visualize them. Okay? And just in case, because that's related more or less, here you have the word prediction, another favorite word of the so-called scientists out there. Let me get back in here. Okay, prediction has nothing to do with science. We don't do predictions. That's astrology. Okay, so if you're into zodiac and reading palms and so on, well, then you can do predictions. Don't bring that into science. Okay, predict is not equal to science. What is science? Explanation. You got to explain something. You got to show that you use your brain. What is a prediction? It's just a description. If you predict that tomorrow at 2 o'clock there's going to be an eclipse, so far you haven't explained anything. All you did was describe. Give me a description saying tomorrow at 2 o'clock there's going to be an eclipse. If I ask you why, now you're going to give me an explanation, not a prediction. What is an explanation? A consummated event. You're trying to explain what happened, how it happened, why it happened. And the only reason you can do that is because you're already familiar with the experience. You've already experienced in this case, an eclipse. That's why you can explain it, because you've seen so many of them that you have an explanation for why that happens. Now you can give me an explanation. If you never saw an eclipse in your whole life, well, maybe you can say tomorrow there's going to be an eclipse. The sun is going to be blotted out. Okay, you can probably predict that. But when I ask you why, you say, I have no clue. Why? Because you have no experience with it. But if you have experience, then you can tell me why, perhaps, right? Why the sun was blotted out. But now you're giving an explanation, not a description. Prediction is description. Description is not part of science. We do not describe, we explain. Okay? So this is the issue. And the reason the mathematicians like to talk about prediction is because that's all they do. Because it's description, and this in mathematics is 150% description. An equation is only a description. You cannot tell me with an equation what light is. That's why mathematical physics has abandoned explanations and calls that philosophy. Dismisses it as philosophy. Oh, that's petty philosophy. And that's why we have no explanations today for rational phenomena that happens out there, for real phenomena. And that's what people want to know. People want to know why, this pen falls to the floor. What causes it to go down? Why does it go up? That's what they want to know. They don't want an equation. They don't want a description. Yeah, I know it goes down. That's a description. Tell me why. And mathematical physics answers, well, that's not part of our job description. That's the answer. Last issue. Here it is. Fellow says, I would say that exists is that what can be experienced. A dream is experienced. So the dream exists. If you wake up and the dream is over, it no longer exists. It no longer exists as a dream, but only as a memory. The memory exists. Bill will spank me for sure. Yeah, yeah. It's like you're saying, okay, my great grandmother exists. So your great grandmother, Bill, you're 68 years old. Your great grandmother must be what, 400 years old? Yeah, she exists. She exists in my heart. But does she exist for you in your heart, your mind, or whatever? No, she doesn't. So it's the notion of ordinary speech. We've never defined the word exists. We just use it. We say, and everybody says, well, I know what you meant by that. She exists in your heart. She exists in your mind. You're thinking about her. That means exists to me at that moment in time. We can't use that word, that definition, in physics, in science. So we have to distinguish the notion of ordinary speech of exist with the notion of physics. Physics is the science of existence. Physics only tries to explain what happened, what happened, and meaning what objects exist that caused it to happen. So physics is the science of objects, and physics is the science of objects that exist. Okay? And so the word exist belongs exclusively to physics. If you say, well, no, in church, on Sunday school, we talk about the existence of God, we don't care. As soon as you mention the word exist, if you want to talk rationally, you cross the line into physics. Now you got to abide by the rules of rationality. And what is rationality? You can't convert concepts into objects. You can't say that love exists, not in physics, not in science. You can say that in ordinary speech. In real world, only objects can be said to exist. They exist if they have location. And with that, I will see you on Wednesday. We'll continue with